So welcome everyone to today's row. It's my pleasure to introduce today's speaker, Bart van Parys. Bart obtained his PhD in control theory at ETH Zurich in 2016, and then he joined as a postdoc to the OR Center at MIT from 2018 to 22. And then after that, he became an assistant professor there in MIT in the Sloan School of Management. Recently, now it's around 3 months that he joined, so he came all the way from Boston to Amsterdam. So now he's a tenured senior researcher at the stochastic uh, group at CWI in Amsterdam. His research is on the interface between machine learning and optimization, and also doing applications like in the area of renewable energy. So it's a pleasure having you here, Bart. And without further ado, I want to give the control of the mic and the screen to you.
Okay, thank you. And of course, thank you for the invitation. It's been, I think, a few years. I remember last time I was in a pandemic and I was also at home. Now I'm home because the trains are striking. So, well, hopefully one day I will be able to present from my office, but it won't be this time. So yeah, thank you all for attending. So I would like to talk about something I've been doing actually with payment. I see is here something we started actually a few years ago, and this is kind of something that I like thinking about, namely the efficiency of statistical methods when we try to make decisions in face of uncertainty. So this work will be kind of an overview of I think two or three papers. The last one is the most recent one. We just published it, but the other ones are kind of more, a little bit older. But I hope you bear with me. Okay. So, I mean, this is kind of a topic that I've been working on for a very long time. You can see here, starting from 2015, I was interested in these type of problems in which you want to make decisions. For example, wind turbine blade control, where you kind of have a system in which you want to minimize load stress by operating some kind of an active element, let's say a flap. And the problem there is that somehow the phenomenon that causes these stresses is actually mostly wind gusts that kind of make these blades vibrate. And the problem is that actually these phenomena are not very well understood. Like we have some ideas that this picture indicates of some power spectrum of these wind gusts, but actually the physical process is it's kind of chaotic and there's not much known. So you want to kind of make a decision which with a model that is somehow inherently unreliable or at least only partially known. Also, and this is kind of the renewable part is something I've been working on already since 2015 on these like optimal power flow problems, thinking about minimizing operational costs, despite the fact that you have this forecast error, especially with renewable energy sources, but you have data. Okay, that's kind of the idea. So I have a little bit of an introduction, but that I hope many of you probably won't need anymore. But I'll just try to spend 5 minutes here. So I kind of work on these like stochastic optimization problems, where the idea is that instead of using the distribution as a primitive, when you try to minimize some expectation, where in my slides I typically use theta for the decision variable and xi for the exogenous random variable. We try to kind of learn it from a bunch of data points. I mean, for the moment being, you can think of them as IID, but you could, have some general stochastic process. But for to keep it simple, a bunch of IID data points, and you want to kind of make a decision based on them. Okay. And so we all know that perhaps the most classical way of doing it is to use sample average approximation or empirical risk minimization, where essentially you replace the unknown distribution by an empirical distribution, and you just minimize an empirical expectation instead. And so the picture indicates that works relatively well as long as this empirical distribution is not too far from the distribution which you sample, something I'll come back to later. And that's actually often the case, but we all know, at least hopefully in this optimization seminar, that if you kind of dive a little deeper, that you have this kind of effect that somehow this approach, although it works, it tends to overfit. And so in my presentation here, I will try, I kind of define overfitting in some sense. There are many ways you can do that. But the way that I will use more or less throughout the talk is this idea that you kind of overfit somehow if your actual cost, the decision, if would kind of measure it with respect to the actual expectation, with this like unknown expectation P, is larger than the cost that you predicted. Okay, so like in this, like the classification example here on the right, you have a classifier that does very well. It had almost zero loss on the training data. It kind of perfectly classifies the red and the green points. But the idea is that then, you suspect that because it's so, so wiggly, you kind of suspect that once you go out of sample, it probably won't behave very well. Okay. And so, I mean, this is work that I've been doing, and many of you have been doing. The idea is that, at least in our community, that kind of there is kind of one way of dealing with this is to minimize a versus expectation. And I mean, the idea is quite simple, and we'll try to come back to that later again, is that you try to kind of capture many distributions around the empirical distribution. And the idea is that you try to consider this worst case ambiguity set large enough so that you kind of hopefully contain the truth. This is something actually you don't really need to. We'll come back to later again. But where you kind of are sure that this predicted cost in this case is a little bit bigger because it's a worst case cost. It's actually larger than the actual cost. Okay, so if that is the case somehow, then you could kind of say that we don't disappoint, right? Like you don't. If you would implement the decision, if you would compare it with the value that you predicted, it's going to be cheaper than your prediction. Okay, so it's like in that case, a nice thing to have, right? The opposite would be worse, in which you think that something is cost $100, but in reality it's 200. That's not so nice. Okay. Now, to motivate this, the first word on my slide is this efficiency. I would like to kind of maybe perhaps spend 1 minute explaining what, as a DRO community, we have been focused on, and that is we have been very much focused on this idea of tractability. So we all know that if you maximize an expectation over a set of distributions, that actually, if you think about it, this is an infinite dimensional problem. And more often than not, if you kind of come up with some arbitrary set over which to optimize, it's not going to be very easy. And so, essentially, the tractability of this approach, hinges on whether or not you can kind of solve this inner maximization problem. Okay? And I would actually argue that for the last 10 years or so, perhaps, the approaches that people have considered have been mostly, or perhaps not mostly, but at least one of the key ingredients there was whether or not they're tractable. And this is something that I would like to go away from. And if you kind of look at my own path, or let's say what we as a community have been doing, it kind of follows that idea of tractability. Okay, so when the animals still talked somehow, when I was doing my PhD, I was working on these like moment-based sets, in which essentially you kind of try to learn from data through moments. And this is, work that has, if you think about it, is now 20 years old, where you can kind of show that if you have mean and variances and you have some loss functions that are not too badly behaved, you can kind of solve these problems. And I actually spent, maybe people already forgot this, but I still remember spending 2 years of my life, trying to make these formulations better. At the time, what we were actually mostly concerned with the idea that if you have means and variances, that the worst case distributions are very pathological. They're kind of discretely supported. And so I spent like 2 years of my PhD talking about maybe we can add some more structure. Maybe we can say that they need to be somehow continuous, unimodal, that their tail has a certain behavior and so forth. Um, but actually, if you look at the literature nowadays, many of these approaches are not used anymore. So maybe you can kind of say that I wouldn't say wasted 2 years of my life, but I spent 2 years of my life doing things that perhaps actually, except for some niche applications now, like in finance and so forth, these things are not really considered anymore. Okay. In fact, this is in hindsight, the answer was pretty obvious in the sense that because these methods they make decisions based on statistics, means and variances, or perhaps some other informations like higher moments, but essentially they only learn from data to statistics. And modern approaches, they try to kind of base their decision directly on the empirical distribution, basically the data minus the order. And actually, if you kind of look back in the literature, I actually found this is afterwards, even people were, Garut Irangar, for example, in Colombia was doing this already in 2006. So, I mean, people already knew that, I guess, before I did. But ever since then, many methods came up, like phi divergences and so forth. But I would say that, still one of the key drivers here is always kind of selecting methods most of the time based on the fact that they are tractable. And perhaps with the only exception of this like LP distance that was not known to be tractable at the time. Most of these approaches kind of became famous because they kind of we were able to solve them. Okay? Um, but on the other hand, I was at the time quite embarrassed essentially that, I spent 2 years trying to make methods work based on, let's say, mean variances. And then suddenly, these new methods came about, in this case, like phi divergence based methods, Wasserstein based methods, which are kind of more intuitive because they learn from data directly. And that kind of motivated my interest in trying to find out efficient methods. Like the fact that, these methods are more, they kind of squeeze more information out of the data than these means and variance based methods. I wanted to kind of understand like what makes a method essentially data efficient. And that kind of led me to this line of work that I would like to present. And so the first part is actually something that is I've been doing. I started with Daniel and Payman, I think in 2021, or at least that was published in 2021. So this is relatively old, but it kind of gives you a nice segue to what other work I've been doing in that direction. And there, the idea is actually quite simple: is that if you want to understand what methods are efficient, it's maybe perhaps good to see of what approaches people have been taking to try to make decisions based on data. And the way it often goes is something along the following direction. Okay. So by the way, if you have a question, please don't feel free to interrupt me because especially on Zoom, it's nice to have questions during the talk, not all at the very end. Okay. So suppose that you have this, you want to make decision based on data, then the typical approach is something like this. So you pick your favorite method, maybe you like Wasserstein or you like some particular type of divergence, and you kind of you pick that particular method. Let's say I'm a Wasserstein person. Let's say you consider this Wasserstein ball, where I for this talk you don't need to know what even Wasserstein is. It's just some kind of distance between distributions. And essentially, you want to kind of understand how large you want to make this radius so that you kind of get some guarantees. Okay, and so the way that you do it is you say, okay, I'll add some statistics to my problem. I can say the data is IID and then sampled from this unknown distribution. Okay, and then what people do is they say, okay, let's.
What people do is they say, okay, let's
I hear myself somehow now. So you open a book on concentration inequalities, or you read the literature and you find some classical inequality that says that the probability that this empirical distribution is close to the distribution which you sample is actually quite high. There's some lower bound for this. It's something one minus something exponentially decreasing in a number of samples where these constants are known, and the idea is that if you want a certain probability of not overfitting, in this case, your probability that your predicted cost is larger than your actual cost, it gives you a tool to kind of make sure that this is the case. Okay. And this is kind of the way that most of us, I guess, at least myself included, have operated. You pick a particular method, and you kind of show that it's tractable somehow, and you try to scale it so that you get some desired statistical guarantee. Okay, and so essentially, what this line of work I will present, it does want to kind of do the opposite. Essentially, what we want to do is we want to somehow start with the guarantee. We don't want to care about what methods that we will pick, and we want to kind of figure out what's the best way to achieve this guarantee. Okay. In fact, stepping a step back, you can kind of think about if you talk to different communities about this problem. I've done that in the past. Is that everything about that I set up till now is that essentially we want to make decisions with data. That's all very well, and we want to protect against this overfitting. Well, many other communities have had the same problem. Essentially, we just try to protect some decision against overfitting. And if you ask the OR community, then perhaps they might say you can try robustification and it definitely works. But if you ask other communities, they actually will not say that. If you ask a standard statistician, you're much more likely to get an answer of why don't you just regularize the cost? And in our community, we know that to some extent it's equivalent, but still, if you ask someone who does deep learning, you can kind of think that there are many other methods that try to protect against overfitting. Think of early stopping or kind of even dropout routines. They might not be as disciplined perhaps as replastification, but they do kind of work. Okay. And so essentially, I kind of was wondering, okay, why do we use robust optimization? And given the fact that in my PhD, I spent 2 years working on methods that perhaps were not efficient, how can I make sure that whatever method I pick today is going to still be kind of a relevant method 10 years down the line? I didn't want to work on something that then ended up being not used. And so I started thinking about this idea of what does it actually mean to be efficient in some sense, or uh, how can we think about some methods being better than others? Okay. And so this is work that I've done with Daniel and Peyon already in 2020. So essentially, we kind of figured out this one way of thinking about proving that these methods you cannot really make them better, at least in some sense, is the following idea. So if you pick a standard method like this scale DRO method, essentially, where you just maximize with respect to a KL divergence, then essentially on a high level, you can kind of say that, well, these methods, they are essentially worst case. So they predict costs for every action and every kind of empirical distribution that are always larger essentially than a sample average approximation. Like the sample average approximation would be like the radius 0, and if the radius not 0, it's going to be slightly larger. Like the picture indicates, it predicts costs that are always uniformly larger than some sample average approximation. But with what you buy with this is that you can get some out of sample guarantee. Okay, so this is something under some regularity conditions, auto loss and so forth. You can kind of indicate that, well, the probability that this thing is too small is not very large, or vice versa, like it's stated here. This method is going to give you an upper bound on the cost with high probability. Like in this case, 1 minus something exponentially decreasing. And you could say, like, well, by itself, this is actually not actually very surprising. I remember about the Wasserstein ball. Well, it satisfied the same guarantee, given that you scale the radius sufficiently large. And so you can kind of wonder, like, well, there's nothing really special about this particular formulation, or any formulation for that matter. Typically, if you make it large enough, you'll get some nice out of sample guarantee. That's not really an issue. So the way that we kind of thought about efficiency is actually to say, well, there's actually a reverse of this statement. You can actually show that, well, if you satisfy this guarantee, and if you predict costs that satisfies this guarantee, then actually you need to be uniformly larger than this KL predictor. Okay, so for whatever decision you consider and for whatever empirical distribution, you need to predict the cost that is always larger than this KL. Okay, so it's always more, in some sense, conservative than this minimal formulation. And so in that sense, it is kind of an optimal formulation. You know for sure that however you predict costs, you need to at least predict the KL prediction. Otherwise, you cannot, in the sense that we defined, avoid overfitting. Okay? At least not you cannot get the same guarantee. Okay? So as an optimizer, you can actually think about this same statement in a slightly different way. You can kind of think about, well, what are we trying to do? We're trying to make decisions by minimizing a proxy cost. This is kind of this, this function C. And if you're interested in having a certain out of sample guarantee, then you want this the probability that you're too low to decay fast, or the probability that you're overestimate the actual unknown expectation to be close to 1. In this case, for example, 1 minus something small, some exponential in a number of samples. And you can think of many formulations satisfying this. Okay, so and in the picture, this orange formulation say satisfies this, but there might be other formulations that satisfy it as well. When you think about the Wasserstein, for example, and given the nature of this guarantee, you can kind of say, well, if there are two formulations that satisfy it, in the sense that their cost is always an upper bound on the actual unknown cost, at least with high probability, then it makes sense to ask for what is now the minimum upper bound, right? Like that's kind of a natural question to ask. And this is kind of asking for, well, what formulation now is the least conservative, given that all of them, in order to get this guarantee, must have some inflated cost. What's the minimal amount of inflation that you need to add to, let's say, a sample average approximation so that actually you get something that is or satisfies this out of sample guarantee? Okay? And so this is a partial order in the sense that there are some models that you can't compare. And so essentially, if you think about this question of finding the least conservative or efficient kind of data-driven decision formulations, you can think about it as trying to minimize or trying to find the least conservative formulation according to this order I just defined that actually enjoys that guarantee that you're interested in. Okay. And because it's only a partial order, we all know if you minimize some partial order, you can get the best typically you can hope for are these like Pareto optimal solutions. Like the picture indicates, essentially every one of these curves is Pareto optimal because none of them dominate the others. So in that case, you cannot really say much more than just all these formulations. They're in some sense equally optimal in the sense that none of them is any better than the others. But we are in some sense lucky because it turns out that this least conservative problem actually admits this kind of dominant solution. So there is there is a solution, namely this KL predictor in some sense, that is somehow the smallest, universally. Okay, so for all the other curves are kind of above it. Okay, so essentially you can think of this formulation as somehow the solution to the problem of like, well, how do you now actually predict costs that are the least inflated? That offer that offer a certain out of sample guarantee at the smallest bias that you can essentially add. Okay. And it turns out that this is kind of relatively old work. Maybe I might have already presented it at some point. But you can actually show that this is not really a result that hinges on this particular framework. You can actually show that even if you relax somewhat, for example, the IID assumption to um, weak dependence. Similar results hold true. Even you could kind of say, well, perhaps this particular guarantee that you impose is not the one that I want. Maybe I want the probability to be just bounded or close to one, not necessarily exponential and so forth. It actually turns out that even in that case, essentially this scale formulation is in some sense efficient. Like a similar results hold also if you kind of consider different types of defining exactly what efficiency actually means. Okay, so this is the framework I worked on, but there's some other perspectives as well. Okay, so the only thing I want to say with it is essentially is that if you just have the sampling stochastic process that I just defined, where you essentially get data from the unknown distribution, you want to make a decision, and you want to have some kind of guarantee of not disappointing, that is the best thing you can do is in that case just this like KL divergence ambiguity set or KL distribution robust optimization formulation, and that kind of falls out naturally. So instead of imposing a certain method and then trying to scale it as good as you can, essentially you try to come up with a set of guarantees that you're interested in and then trying to kind of reverse work your way backward. What should that method now look like so that I can get that guarantee as cheap as possible in some sense? Okay. Now, many of you are expert in this area. You all know that, well, if that what I said was true, and I know it is, why don't we actually kind of see that in practice, or at least in the literature? If you look at the literature, you would expect that, well, given this result was published, I think in 2021 or so, that now everyone does like KL robustness, but this is definitely not the case. And we've been trying to think about what exactly, why that is. And this is a paper that I've done, I think, not 1 or 2 years ago with my students, trying to think about why is it that these formulations actually don't, practically work as good as somehow theory suggests. Okay. And maybe one observation that you can make, and this is, if you're familiar with this, like KL distance is a pretty standard observation, is that this distance is relatively badly behaved in the sense that if you take the KL distance between two distributions, uh, the same distribution, let's say, then of course it's zero. It's kind of one of those, fundamental properties. But the idea is that if you kind of slightly shift that distribution, let's say to the right over some negligible distance, then essentially you immediately get that the distance becomes infinitely large. Okay, so this is just a complicated way of saying that the distance is not continuous. And at the first glance, you might think, or at least I always thought about this cannot possibly have any repercussion in a practical situation. But the problem is that because of this this discontinuity in some sense, is that if you kind of look at the guarantees these methods offer, once, for example, there is a shift between, let's say, training data and data out of sample, that all these nice guarantees that we talked about essentially immediately evaporate because there is no more guarantee that if your data samples are sampled from one distribution and your out of sample data from a distribution that is basically the same up to like a very small shift, then nothing actually carries out anymore. You don't have these nice out of sample guarantees. And methods, for example, such as the Wasserstein distance, they don't actually have that shortcoming. So they are nicely, you can show that they're nicely continuous, at least if you have some moment conditions. And so that means that essentially these methods, they naturally have some, or they offer some protection against, this idea of distributional shift in your data. Okay. Now, like I said before, I care a lot about efficiency, and so at that point I thought that this might of course be true, right? Like if you think about that Wasserstein distance, of course it does actually offer protection against the distributional shift. But does it actually do that in an efficient way? Is it true that somehow that the protection it adds is somehow added efficiently? Maybe there are some other better methods out there that can achieve the same thing but cheaper. Okay? And so essentially, we know, like I've tried to indicate in the previous part, is that if you just have statistical error, so the only error that you have is basically caused by sampling, that the KL distance works amazingly well. It has, this type of efficiency as guarantees. But the moment you add more, let's say, data inaccuracies, nothing works anymore. For example, if the data samples that you get are slightly corrupted, if you on every data point you can add some epsilon bounded noise, it doesn't work anymore. So this is kind of a natural observation model in which you actually don't get to see the actual data points, but rather some corrupted versions. Or, for example, you can think about the classical model in robust statistics, for example, where a small fraction of your data points might not even be just a tiny bit distorted, but arbitrarily bad. Okay? And given these two models, the question is like, is it true that somehow these methods that we discussed offer efficient protection against these two things? Okay? So we know that, for example, just to recap, the KL formulations are efficient against statistical error. So if the only error that you have or that you believe you have is just statistical noise, then that's what you should do. There's actually really no reason to use anything else. If you think about Wasserstein distance, then I try to kind of sketch it, try to understand what it does. Is you can think about it as a method that essentially protects against noise. So like if the loss is concave, then you can think about this distance as maximizing the loss, where you kind of perturb each of the data points in such a way that the total perturbation is on average and norm not small, not bigger than epsilon. Okay, so it's not exactly the same noise model as we've seen, but it's kind of a believable noise model, so you can kind of think about it as offering relatively efficient protection against only that that type of phenomena. And we also know, and this is kind of the difference here, that rightly scaled because of these concentration inequalities, it does actually also offer protection against statistical error. But my claim is this is not efficient. So if you only care about statistical error, then KL is better. It's just because if you want both statistical error and noise, then perhaps something like a Wasserstein is clearly better because at least it does to some extent both at the same time, somewhat adequately. Okay, but still, the last problem is contamination, where samples can be arbitrarily corrupted. Actually, neither of these methods does very well with this. And so the question we asked is like, can you actually derive methods that are efficient against all three of these types of overfitting phenomena? We call them simultaneously. Okay. And actually, the answer is maybe perhaps embarrassing straightforward. Yes. By just essentially combining several strategies, namely, like I tried to communicate in the first part, if there is only statistical error, if the only cause of deviation, let's say, between the actual distribution P in red here and the distribution of the samples, this Qn, is only caused essentially by sampling, then we know that KL is kind of the right distance metric to consider. And this is kind of, if you look at the proofs, this is essentially based on this large deviation Zanoff theorem that I stated on the bottom of the slide. But the idea is that essentially it captures typical observed distances between the empirical distribution and the one that you sample from. Now, in this new framework, we actually allow for further corruption. So the idea is that, well, perhaps in reality, you never actually get to see the samples that are from that distribution, but rather each of these samples might be corrupted by noise. Okay, so there could be some small noise term, in this case delta, added to each of these observations, and hopefully that has a small norm. And we also assume that maybe a very tiny fraction of those samples is essentially just completely corrupted. Okay. And so the question is, in that case, well, if that's true, then there's of course a distance between the clean empirical distribution, this Qn here, that you don't see because you only get to see essentially the corrupted distribution, this Pn. And the question is how to describe the difference between those two. And so we kind of figured out relatively quickly that the right distance to use here is what we call a generalized Levy-Prohorov distance, where essentially on a picture we say that these two distributions are, the one between the empirical distribution of the clean data Qn and the one of the dirty data or corrupted data Pn. They are close if you kind of can find, that's what I try to indicate on the picture. I hope it's clear. A joint distribution that puts essentially at most alpha mass outside of a cylindrical strip around the diagonal. Okay, so it turns out that this is more or less an even only F condition, meaning that if an adversary can only perturb an alpha fraction of the data and can add epsilon bounded noise on each of these samples, then these two distributions, the empirical ones of the clean and the corrupted data, they need to be close in this distance, and vice versa. So it's an even only if condition. Okay. And so the kind of idea is now quite clear in the sense that, well, if we know that the KL describes the effect of statistical error, and we know that this Levy-Prohorov distance describes at least the effect of the noise, the extra noise model that we discussed, then essentially what you should do, and this is maybe in hindsight maybe obvious, is just combine these two distances. And so you kind of we propose this holistic robust formulation where essentially you say, well, instead of using only the KL divergence, what you do is you kind of combine it with this like Levy-Prohorov distance that essentially adds protection exactly against this noise and contamination model that we suggested. Okay. And that actually works. So you can actually show that if you do that, then as long as the parameters are chosen well, in the sense that the adversary can only add epsilon noise to each data point and can only corrupt a fraction alpha of them completely, then if you use this kind of method, then you cannot overfit, in the sense that the probability that you overestimate the unknown expectation is, high, as 1 minus something exponentially fast, where you can kind of control this decay by choosing the radius r. Okay. So exactly the same statement of KL, where in that case you didn't actually have this noise and contamination. And it's essentially also optimal or efficient in the same sense we defined before, namely that, well, if you have any other methods, it doesn't need to be DRO, but just any proxy loss that you want to minimize that satisfies this anti-overfitting kind of criteria, then you actually need to be at least as conservative as this formulation we suggest. Okay, and so in some sense, what I wanted to say with this is that, well, instead of using a formulation that kind of is good in, let's say, protecting against overfitting in terms of statistical error and some kind of noise model adequately, you might as well just go for something like this, where you describe your noise model, where you kind of impose a statistical guarantee you want, and you try to kind of kind of deduce backwards, well, what type of formulation do you actually need? Because in that case, we know that there's no better formulation. We kind of already know what you need to do if you want to somehow squeeze as much out of data as possible. Okay. Now you could say, and this is something, a remark that I get a lot, is that yes, you have an optimal formulation, but you have several parameters that you have to estimate. I would say that is true. So one downside of this method is that you need to kind of know how much noise and contamination you want to protect against. There's no real way of learning that from data, at least not that I understand it. So you should think about it more as something that as a decision maker, you have to be comfortable with. If you really believe there is no noise, then you shouldn't kind of add protection against noise, because of course it will make it slightly more conservative. Okay. I wanted to say, before I go to the last part of my talk here, something about tractability. You can actually show, and this is kind of quite surprising, because even in the case where you don't have KL divergence, so you set R to 0, and in a special case where alpha and epsilon are equal, so basically you believe that there's as much norm-bounded noise as there is a fraction of the data corrupted, then even in that case, there was no known formulation. This is actually the case that was studied by Garut when he did this Levy-Perhoorov paper. But we found out a way to do it that is actually at least as tractable as just using some standard Wasserstein formulation. So I won't go over the details, you can ask me offline, but the idea is that as long as you can kind of compute these like inflated loss functions, L epsilon here on the slide, well, you're kind of okay. And these functions you have to compute anyway if you want to do something like a Wasserstein. Okay. Okay, so that brings me to the last part of my talk. I think I see I have only a few minutes here, where people always ask me, well, you kind of talk a lot about these contamination, in the sense of a certain fraction of your data points can be corrupted. What has that to do with robust statistics? And I always used to think probably not much. But actually, I found some ways in which I think that there is actually now a little bit of a clear understanding of how these two are related. And the way that they're related is actually to imposing essentially parametric assumptions on what data distributions we consider. In the sense that if you think about the classical problem for which the median, for example, is derived, is the idea that you somehow get data points from a parametric distribution. Think about a Gaussian distribution, where you want to estimate some unknown mean. So you get some data from a Gaussian where you don't know the mean. But unlike the classic situation where you have just the data points, just like we had before, there is an adversary essentially that can kind of perturb the distribution from which we sample. In the sense that instead of getting data from an actual Gaussian, we get data from something that looks, at least in total variation distance, close to a Gaussian, but it's not a Gaussian. Okay? So that means a total variation that you can kind of move an alpha fraction of your mass to an arbitrary location. Okay? And then, of course, you still have statistical error in the sense that you sample n data points from this. Okay? And so the classical location estimation problem is solved in some sense if you have no noise, and we know that the empirical mean is kind of optimal in a way that I will come back to later. But we also know that if you have corruption, then the mean is terrible, because if you have one data point that is very far away, you can kind of arbitrarily move the mean to whatever location you want. And so, it's kind of suggested in that case to, for example, use something like a median because it's less sensitive. But since, this is kind of seminal work by Huber, we actually know that there are better or efficient ways of dealing with precisely this problem. Namely, if you think about the Huber estimator, I won't kind of exactly say what it is, but it's essentially an estimator that just returns essentially the mean of the data points, and where essentially instead of weighing each data point equally, you kind of reduce the weight, like the picture indicates, from 1 over n if it's close to something that is smaller than 1 over n if they are kind of far away. So essentially, something that is very much an outlier will get a far smaller weight than something that is close. And so you try to reduce the sensitivity of this estimator to things that are kind of far away. Okay. So what do I mean by why is this a better method, let's say, than the median? Well, you can kind of think about these estimators as what is the quality of this estimator? Well, you can kind of think about it as having an error margin. And on the picture, I mean, there's kind of a formula on the bottom here, but on the picture, the error margin is essentially the smallest interval that you have to construct around your estimator to be sure that with some high probability, it will actually contain the true unknown mean. Okay, so the estimate, the guarantee says that the probability that it's not in there, or that it's in there, sorry, is something that decays, is 1 minus something that decays very fast. Okay, and so we all know that, for example, the error margin of the mean is very bad if you have corruption, because you know that you can kind of shift the mean to any arbitrary place. It actually doesn't have an error margin. There is no bounded set around the mean that you kind of know with high confidence that you actually will contain the unknown expectation. While the median is much better. It has actually a finite error margin, meaning that you can kind of construct a finite set around the median that with high probability actually contains the unknown expectation. Okay. Now, in what sense is this Huber estimator the best? It's optimal in the sense that it has the smallest error margin. So among all estimators, it kind of is the one such that if you consider an interval around it, it will contain the truth with a certain kind of guarantee for the smallest interval possible. Okay. That kind of brings me to what has this to do with these DRO predictors I just talked about. Well, you can kind of think about the predictor that we had before. You can kind of translate it into this setting by combining it again, the KL distance for statistical error with the appropriate error metric, which in this case was this total variation. You kind of define this a set that you hope contains the actual unknown expectation as I did it on the slides. And so maybe just to kind of give you an indication, you kind of the way you should read it is that I'll suppose that you get this red distribution as an empirical distribution or something that is close. You kind of say, well, when is a particular point, let's say particular parameter in that set, well, you can kind of construct a normal at that position, and then you ask the question, can you find this PC, this kind of corrupted distribution that is close to this Gaussian, but it is also close in KL to the distribution I actually see in the red one. Okay, and if that is the case, then it's in that set, and you can do that for several positions. Some parameters are in a set and some are not, and so you can kind of get some confidence set because it gives you a set of parameters that you think contains the truth, but you're not, that's the hope at least. Okay? And so you can actually show that this is not necessarily an interval, so this is it can be a non-convex set, but it actually is somehow minimal in the sense that we know that it, with an asterisk here, is actually a small technical condition that I don't want to talk about, but with high probability, it actually contains a true unknown expectation. And it's also minimal in the sense that, well, any other estimator or let's say set predictor that is satisfies this high confidence guarantee must be at least containing this like DRO set. So in some sense, if you would predict a smaller set, they wouldn't actually satisfy this guarantee anymore. So it's kind of optimal in the same sense as we discussed for this KL formulation or this holistic robust formulation before. Okay. And so in some sense, it kind of solves this like find the smallest possible set that contains the true expectation with a particular type of statistical guarantee, namely that the probability that it's not in there is small. It decays exponentially fast. And it's again Pareto dominant. There is no other way of doing it somehow. Okay. Now that brings me back to the question: what has that now to do with this like classical robust framework of Huber? So we can actually show that in some sense this Huber predictor is another type of solution, namely it's a minimax solution in the sense that there is actually one worst case scenario in some sense where this minimal set is at least as large as the confidence set predicted by Huber. So they kind of like this orange line indicates that they touch at least in one of these worst case distributions. Okay. And they touch, meaning that the diameter of the set that they predict is equal, meaning that we know that this scale, this ambiguity set is always smaller, but there's at least one empirically observed situation in which essentially the width of the Huber set and the width or the diameter of this KL set is actually exactly the same. Okay, so these distributions look like this, by the way. They kind of look a bit crazy, but you can show that if you compute the Huber mean, because it's symmetric, it's zero. If you take the interval around it, you get this nice interval, and then you can prove that essentially the KL set needs to contain at least the two extreme points. Okay, so that essentially is the proof. What I wanted to say is that at least it gives you a direct connection between robust statistics and this set, in the sense that once you add this parametric assumption of normality, it actually recovers in some minimax sense essentially the classical work of Huber, for example. That is not to say that you should use this set in the sense that, like I said before, once you add parametric assumptions, you get these non-convexities. So I'll try to indicate that on this picture. While the Huber set is a nice interval which you can optimize over and which is nice, these sets can be quite hard to optimize over because they can be many disjunct intervals. So it's not always clear that it's very practical. Okay, with that, I think I want to conclude. So I think how long have I here? Maybe I went a few minutes over time. I'm very interested in making decisions efficiently. Like I said, I don't want to waste 2 years of my life anymore without knowing that what I do, at least we have some idea of what the best method looks like. I also kind of are interested in the idea of, well, if you want to kind of add a real life protection, like this holistic robustness, it might be better to just figure out what type of protections you need and work backwards rather than come up with a new ball and show that it is actually in some sense robust. And I try to, maybe in the last part, try to kind of indicate that these kind of classical methods that deal with these, contamination models, they in some sense are recovered by this framework as well, at least in the way that I discussed on the previous few slides. Okay, so with that, I think I want to kind of stop. And so if you have questions, I think I have at least until a little bit after 4 to answer potentially any doubts or remarks.